All right, so hello everyone. I'm Norman Wahlberger, and today we're going to talk about the sine rule, which I was going to do last time, but I didn't get around to it. And then we'll talk about continuous probability distributions. So we'll extend our theory. Right now we're just really talking about discrete probability distributions. We want to extend that to include continuous ones too. Especially we're interested in the normal distribution, which is probably the most well-known and studied distribution of all. Okay, so let's talk about sine rules, which is an application really of understanding a little bit about the binomial distribution. So let me just remind you there that this distribution BNP, all right, this is a distribution that comes about by flipping a coin. There's a coin, and we flip it in the air, heads or tails. And we'll suppose that it's a weighted coin so that the probability of heads is, say, p for some random number between 0 and 1. That's fixed. Doesn't have to be a half. And then this distribution comes about by tossing this coin n times and asking, or defining pk to be the probability of getting k heads from n tosses of this coin. Okay, and we had a formula for that. So it was n choose k. That's sort of the number of subsets of size k from the n possible tosses. And then we are interested in getting heads k times, which has probability p to the k, and not getting heads the remaining n minus k times. Okay, and sometimes we define q to be 1 minus p. So we could also write this as n choose k, p to the k, 1 minus q to the n minus k. Okay, so these probabilities are a little bit challenging to calculate without a calculator, because if k and n are large, then these you're looking at big powers of some probability, and these numbers can also be relatively big. But nevertheless, with a calculator, it's not so bad. So let's look at an example. So we have a tennis player, say Sue, and she usually wins 60% of her tennis matches. Okay, so this year she gets a new coach. So this year with a new coach, she wins 12 of 15 matches. Okay, which is amounts to 80%. And so she wonders, well, I've gotten better. I'm winning 80%, but it's only 15 matches. Is that enough matches to be able to tell whether the coach has made a difference? She's interested in knowing, does the new coach really make a difference? Well, it's hard to say exactly, completely certainly. You know, there's a bit of possibility one way or the other, but there's a way of looking at it from this binomial probability point of view. So what we do is we think about her winning a match as a random event. Okay? So we think of the probability of Sue winning a single match is, well, p, and that's, we're told, 0.6. So Sue winning any one match is a little bit like tossing a coin. That's weighted 60% towards heads. Okay. All right, and what are we interested in? Well, out of n equals 15 matches, we're interested in what is the probability of her, the probability of winning Well, not just 12, but let's say 12 or more matches is, well, P, the probability of winning 12 plus the probability of winning 13 plus the probability of winning 14 plus the probability of winning 15. Where we're talking about this binomial kind of distribution where n is 15 and p is 0.6. Okay, so in terms of this binomial distribution, that's a sum from k equals 12 to 15. Any one of these is 15 choose 12 times p, which is 0.6 to the k. And I'll put the other one here. Not 0.6, rather. There's the probability of her winning one match. And then the probability of her not winning a match is 0.4. And if that's going to happen k times, then this has to happen 15 minus k times. So that's just using the formula. There's 4 terms in that series. These are just the expressions for the various probabilities. Yeah?
Is that going to be 15 choose k?
15 choose k, yes, thank you. I don't know where that came from. Thanks for the correction. So this is 15 choose k. So let me say it again. Sum from k equals 12 to 15. 15 choose k times 0.6 to the k times 0.4 to the 15 minus k. Thanks. Okay, and then you can get your calculator to work that out. And that is roughly 0.091. Okay, which in terms of percentage, that's a probability. In terms of a percentage, that would be roughly a 9% chance. Okay. So in other words, if you asked the question, you were just flipping this coin, and you were going to flip it 15 times, what's the chance that you're going to get 12 or more heads if the chance of one head is 0.6? And the answer is it's about a 9% chance. So if the coach didn't make any difference, there would be a 9% chance of her getting a result at this level or higher. That's relatively small. It's not completely negligible. But it's suggesting to us that probably it wasn't chance, that probably her coach had something to do with it. Okay, so the conclusion here would be that probably the coach improved her chances. She's probably playing at more than 0.6 now. Okay, so probably the coach has really improved her game. And of course, if we did a slightly different example and this number was much smaller, then you could be more and more confident. The smaller this number is, the more confident that you can say this is very unlikely. Okay, so a similar kind of reasoning, application of the binomial distribution, is to this example with corn yield. So it's an example of what's sometimes called the sine rule. Okay, it's a very simple-minded, almost simplistic kind of analysis of a situation, but it at least gives us an orientation to a practical problem. Okay, so the story is this, that we've got, let's say we're a farmer, and we know that the average yield of an acre of corn is, let's say, 110 bushels. Okay, on average, 1 acre gives you 110 bushels. And then someone comes along with a new variety of corn. So a new variety is planted in 18 acres, a new variety of corn, yields the above for 18 different acres. So you've planted 18 different acres of this new corn, and these are the yields that you've gotten. So in one of the acres you've got 113.4, and another one you've got 115, and so on. These are the 18 yields, and you want to know, is this new variety of corn actually better? Okay, there might be a little bit of uncertainty, but we want to make some kind of judgment about whether it's better or not. So the idea is very simple. What we're going to do is we're just going to compare each of the values with the expected one, the 110, and say whether it's bigger or less than the expected one. So the method is assign plus and minus to each reading or value, depending on whether it's bigger or less than the expected value. Which is 110. In other words, we think of this as a little bit of a random thing. Okay? So here there would be a plus. That's more than 110. That's more, that's more, that's more, that's more. That's more, that's more, that's more, that's more, that's more. Oh my goodness. Oh, that's less. Okay. Oh, this one's less. Yeah, 106 is less. Oh my goodness. Okay, how am I doing now? This is more. This is more. More, more. Oh, this one. No, that one's all right. Oh, here, yeah, okay. Don't trust a mathematician to do basic arithmetic. Okay, so we've compared these values to our average value, 110. We've checked our computation. We see that we've gotten how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 pluses, and 1, 2, 3, 4, and 4 minuses out of a total of 18. Okay, so suppose this corn was no improvement. Well, suppose it was just a regular corn. Then you could kind of imagine each acre is a bit like flipping a coin. It could be more or it could be less than the average or expected value. And you expect half of the time it would be more and half of the time it would be less. So if the probability was 50-50 each way, what is the likelihood of getting such an imbalanced outcome? In other words, we want to make a calculation that essentially compares this with a binomial. So we're going to be looking at the binomial with 18 readings where we're assuming the probability of 0.5. Okay, and we're going to ask the question, what is the probability of getting, well, maybe not 14, but 14 or more heads? 14 or more heads from these 18 tosses of the coin. So it's a little bit like the previous example. We have to make a computation and then stare at the number that we get. So what we're actually interested in is the probability of getting 14 plus the probability of getting 15, 16, 17, and 18. Those are all the possible values up to and further on from what we're considering. In summation notation, that would be the sum from k equals 14 to 18. The binomial, well, we have 18 choose k. In this case, we're assuming that, for the sake of argument, that's an equal probability each way. So 1/2 to the k and 1/2 to the n minus n is 15. To the 15 minus k. Oh, 18, yes, 18. Thanks. Okay, we want to calculate this. Oh, this is a little bit simpler. I mean, this is 1/2 to the k and 1/2 to the 18 minus k. That's just 1/2 to the 18. So we can certainly simplify this by bringing that out. So 1/2 to the 18. Put the 18 down there. And then the sum from k equals 14 to 18 of just these binomial coefficients, 18 choose k. And that turns out to be pretty close to 0.015. What is that? That's the probability. If you flipped a coin 18 times, the probability of you getting 14 or more heads. And the probability is about, in terms of percentage, 1.5% chance of getting 14 or more heads from the 18 tosses. From 18 tosses of a fair coin. So that would be like someone coming and saying, I'm going to toss a coin 18 times, and they end up getting somewhere between 14 and 18 heads. You think this is very likely not a fair coin. It's biased. And that would probably be your conclusion here as well, that because this is such a small probability, the probability that it really is coming from a p equals 0.5 situation is rather unlikely. So the conclusion is that this yield of corn is probably an improvement. The new corn, the new variety, is better. But we shouldn't put all our money on it. There's still a 1 or 2% chance that it's purely due to luck. All right, so we have to be a little bit careful extrapolating from evidence. Just because something is works 14 out of 18 times, it doesn't necessarily completely determine that it's biased. It could just be luck. Of course, this is also a little bit simplistic in the sense that we've completely avoided talking about how far above the average each one of these yields was. We just said greater or less than. So it's obviously a pretty simplistic kind of test, and you'd expect that as you learn more statistics, there'd be more sophisticated things that you could do, for sure. Okay, but it's at least a first kind of thing to try to get a ballpark idea whether something's likely or not. Okay, so now we want to move to continuous probability distributions. So up till now, we've been talking about discrete situations. Well, we're talking about discrete situations. And that means, well, often we have finite sample spaces. And we're measuring. Measurements is really like random variables that take on discrete values. For example, flipping a coin and counting number of heads. Okay, that's obviously a natural number that you're going to get, or an integer anyway. But there are lots of situations where we measure things which are not necessarily expressed in terms of integer outcomes. Lots of situations where there's distributions involving a continuous possible range of measured values. So that means we have to actually adjust our thinking a little bit and terminology, and some calculus comes into play. We end up having to replace the sums with integrals. Okay, so let's do an example. So suppose I'm interested in how much cash an average student at UNSW carries around with them. Maybe I'm a sociologist or an economist. And so I'm going to interview you all. I'm going to ask you to count your change. I'm not going to actually do this, but I might ask you to count how much money you have in your wallet, in your pockets, all the change. And then I'm going to record all that information, and I'm going to ask lots and lots of students. Okay? So I might be interested in a population. S might be the students at UNSW. And I might be interested, out of all the possible questions, I might be interested in the random variable that is equal to the amount of money in a student's pocket, or a student's wallet, or purse, whatever it is. Okay, so I'm going to record those outcomes. Well, I don't know how much I should have put on the scale. I mean, probably some students have $100, maybe more. Maybe they've just gone to the ATM to prepare for a good weekend. They've just taken out some money. All right. On the other hand, maybe it's been a long time since they've paid, and they're still waiting for their next paycheck, and it's down to this end. Who knows? So I ask a lot of you, and I start, collating the data. So maybe one person has $32.49. Okay, so I'll put an X there. And then the next person has $73.47. I'll put an X there. And I'll start marking all these X's. Here's a rich person. All right, the X's themselves, any one X or two X's are not that interesting. But what is interesting is the underlying distribution. Once you start having enough data, there becomes some kind of pattern available here. Some pattern becomes visible. It's not likely to be random. I don't actually know what the distribution looks like, but my guess is that it might be something like that. Maybe. And it's not really very useful for me to represent this with lots of little bars. I could do that, count exactly how many cents. I would rather represent it by a continuous function rather than hundreds of little bars. Okay, so there's a certain function that's occurring here that we don't know what it is until we actually make some measurements. And this is playing the role of the probability or frequency distribution. And it's called the probability density function. And let's give it a name. Let's call it, say, P of x. And what should this function's properties have? So this probability density function should have the property that, first of all, it should always be between 0 and 1. That the total probability should equal 1, just as in the discrete case. Well, the total probability in this case would be an integral. All right, in this case it would be from 0 to infinity, but maybe I'll just go from minus infinity to include the general case. So the total area under this function, integral px dx, should be equal to 1. And the interpretation is that if we have any one particular interval, let's say, from A to B, there's a certain interval. There's the interval A, B. That the probability of our variable x being or taking values in A, B should be really just the total weight of the function above that interval. In other words, I should just calculate this area, and that area should represent the probability of the variable x that I'm interested in of falling in that range. So I should put here the integral from A to B of this probability density function P of x dx. So this is a continuous analog of the discrete type probability distribution that we talked about earlier, where we had values, or let's say probabilities, P1, P2, up to Pn on the values x1, x2, up to xk. So in that case, remember here we require that each of the individual probabilities was between 0 and 1, and that the sum of all the probabilities was a total of 1. And if we wanted to know what the probability of an event was, so if E was a subset of, well, let me say it this way. That the probability of x taking on being in the set, say, xi1 to xil would be the sum of the pi k equals 1 to l, the associated probabilities. So what we're doing over there with this continuous distribution is mimicking the finite one. All right, so a simplest example, I suppose, is the uniform distribution. That's a distribution that looks very simple. we have two numbers A and B. And this distribution is going to have the value 0 outside of A and B. And it's going to be constant along A and B. And then it's going to be 0. So here's this probability distribution P of x. And it's equal to 0 if x is less than A. It's 0 if x is bigger than B. And it's constant between A and B. And what must that constant be? There's only one choice for that constant, because the total area has to be 1. So the constant has to be 1 over B minus A if x is between A and B. All right, so this would be the value here. That probability would be 1 over B minus A. And suppose we wanted to know what the probability of a sub-event was. Say, suppose I choose C and D inside here. So then the probability of x, whatever the random variable is, the probability of that being in CD would be the integral from C to D of this function P of x dx. And if A is less than C, is less than D, is less than B, so if we have a situation that looks like that, then this probability, this would be the integral from C to D of this constant, so it would just be D minus C over B minus A. That would be the integral of this little uniform function from C to D. Okay, so what did we do for discrete random variables? We can do now for continuous random variables. And what was it that we did for discrete random variables? We defined the two important numbers, the expected value and the variance. So we're going to do the same thing here. Well, let's say for a continuous random variable. Okay, so the official setup is that we still have a sample space with a probability on it. It's still a probability space. We still have a function on it. And I'll lay out the values of the function horizontally now. But now instead of this function taking on a discrete possible value, it can take on any one of a continuous range of values. And it might be in an interval, or it might be on the positive axis, or it might be across the whole number line. And then that probability distribution is represented by this function, this density function. The probability distribution function that we've been talking about, also called probability density function. And its key properties, I remind you, are that it's always positive, it's between 0 and 1, and the total integral is exactly 1. And you can think about this as being a probability distribution, or you can think about it as being a mass distribution. It's sometimes useful to think about it as a mass or a density, telling you how dense maybe how dense a rod is at various points. It's another way of thinking about it. All right, so now we're going to define the expected value of x. And it's also going to be called mu. And physically, it's going to be a number which is where this thing balances. Although it's a continuous rod, it's not a finite number of weights. It's a continuous weight distribution across the line, and it will balance somewhere, and that place is given by an integral instead of a sum. So it's the integral from minus infinity to infinity. And what should we put there? Well, the sum in the discrete case was the sum of the values times the probabilities. The sum of the xi's times the pi's. We're going to do exactly the same here. The continuous analog of that is the integral of x times p of x dx. We're adding up values times probabilities and summing it up. Values times probabilities integrated up. And if you know some physics, you know that's how you would calculate the center of mass of this if it was a rod with this as its density. That would be the place where the rod balances. And you all know that trick with if you have a long meter ruler, how to make it balance. You just get your two fingers to hold it like this, and then you bring your fingers together. You ever done that? So yeah, you just take a meter, and in fact it doesn't matter. The mass distribution doesn't matter. You can balance things on top of it. You get a meter like this, balance things on top of it, hold it out like this, and then you can just close your eyes and just bring your fingers together. And when they're together, the thing will be balanced. And that'll be the center of mass. You can try it out. I'll try it out with this. Maybe it's not so impressive. Okay, it has to roll. Okay. So, okay, here we go. I'm not doing anything purposely. I'm just moving them together. If my fingers were narrower, it would still balance. And if it was very long and uneven balance, you can try it at home. And that's what we're calculating here with this integral. We're calculating the center of mass or the expected value of this distribution. And it's called expected value, or mean. And of course, then we also need to define the variance, which is telling us sort of how far apart or how spread out this mass distribution is from the mean. That's also denoted with a sigma squared. And it's just the continuous analog of the formula that we had for the discrete case, which is the integral from minus infinity to infinity. Remember what we did in the discrete case? We took the sum of the difference between the x values and the mean squared and sum that against the probabilities. So we're going to do exactly the same thing here. We're going to take the difference between the x values and this fixed mean that we've already calculated, So we're calculating the differences between x and the mean and squaring that quantity. And then integrating it against the probability distribution, P of x. And that's called the variance. And then sort of as an afterthought, we define the standard deviation as just the square root of the variance. That's the standard deviation. In terms of units here, this is really in terms of like length squared units, because the probabilities are sort of don't have any units, but x has length units. So we're having an x squared here. This is x squared. And when you take the square root, then we're really getting a quantity that's natural units are in terms of length. So in a diagram like this, you will often maybe see a diagram that shows the standard deviation. Of course, that'll be sigma. On a diagram like this, we say that then this is one standard deviation away. It's a measure of how far from the mean this thing is centered. If the sigma is small, it means that all of the weight is pretty close to here. If the sigma is large, it means it's spread out over a long range away from on either side of the mean. All right, there's some transformation formulas that are quite interesting. So that's concerning what happens when we take a random variable x and we cook up a new random variable by adjusting it. And typically what we do is we say multiply it by a and add b. Let's think about those things separately in two stages. So the expected value of just x plus b. So if you have some function, let's say the amount of money in your pockets. Suppose that the average value or expected value was $23.19. And then suppose that I measured the amount of money plus $10. I added $10 to all of your totals. Yes, that'd be a good thing for you, not maybe for me. Then what would be that new expected value? Well, it would just add 10 to the average. Then instead of having $23 and whatever it was, the average would be $33 and whatever it was. So the expected value would just augment in an obvious way by being incremented by b. On the other hand, if I multiplied all of your monies by a factor, say 4, then sort of obvious that the expected value, the average, is also going to multiply by 4. And that's indeed the case. And these are simple exercises that you can get from just the definitions. What about the variances? How do they change? So if we take the variance of x plus b, what do you think happens to that? That's a measure of how spread out from the mean these values are. And if I shift everything over by 10, they're not going to be any more or less spread out than they were before. The variance is going to stay unchanged by a translation. So this is exactly the same as the variance x. However, if I multiply by a factor, well, you can sort of see here that this is quadratic. If I multiply x by a, then mu, we've said, is also going to change by a. So this whole thing here is going to change by a squared, and there's going to be an a squared coming out. Because it's kind of a quadratic thing. So that means that the effect of multiplying by a on the variance is to multiply the variance by a squared. Okay, so we get a squared times the variance of x. In terms of the standard deviation of x plus b, well, that's just going to be the same as the standard deviation of x. And the standard deviation of x plus a times x will be equal to a times, or actually absolute value of a times the standard deviation of x. All right, so these are all going to be important when we talk about the most important probability distribution next time, which is the normal distribution. Okay? The normal distribution is what's usually called a bell curve. And it arises in many, many different situations. For example, if I toss a coin up in the air, straight up in the air, and I let it fall, and then I measure how far it is from where I'm standing originally, then very likely it'll be a normal distribution. Of course, test results are often a little bit like this. In this case, the probability distribution is so special it gets a special name, 5x. And the formula for it is interesting. Okay, it's e to the, okay, in the usual form there's e to the minus x squared over 2. And there is a factor in the front, which you'd probably never guess if you hadn't seen it before. Okay, the factor is square root of 2 pi. Okay, you all know the exponential function just looks like this. And the negative exponential is like this. And so if you're looking at just positive values, the negative exponential, has the value up to 1, maximum value of 1. And so if you're going to square something, you're going to get something positive, and then if you put a minus sign, you're going to get something negative. So this is always negative. It's sort of like, so you're getting something between 0 and 1. And it's symmetric about 0. Takes on a value pretty close to about 0.4. And why do you think the square root here of 2 pi is here? Yeah.
Is it because when you have x squared over 2, then it has 2 pi in it?
Yeah, that's exactly the reason. That the integral of this thing has to be 1. And it turns out that if we didn't have this thing here, a non-trivial calculation, which is really sort of a second-year calculation, okay, you don't do it in first year, but in second year you learn how to do it, is that the integral of e to the minus x squared over 2, there's no formula, you can't integrate that directly. But it turns out that you can still integrate its total integral. It turns out to be root 2 pi. So you need this 1 over root 2 pi to make the whole integral equal to 1. Okay, so this is the normal distribution that plays a huge role in statistics and in lots of things. So we'll talk about it next time. It's the best example of a continuous probability distribution. See you then.